Hello, Mrs. Reynolds. Thank you very much for attending our presentation. My name is Jan, and I'm a business analyst with BookSense. Our presentation is about click-through rate. What is the purpose of our presentation? We are going to discuss data modeling with two algorithms, logarithmic regression and k-near neighbor, KNN. Our company is in the online ad industry, which is growing at a rate of 160 billion per year. BookSense.com has 300,000 users, and these users get free and discount book offers, and we are making money by selling ad placements, which are dependent on click-through rate. The data modeling that we will be presenting to you today is based on 50,000 emails of historical data, about 93% of which are no clicks or zero for the Y click variable, and 7% one, which means people click through those emails. Our task is supervised machine learning, which is an algorithm that relies on labeled input data to learn a function and produce output given new unlabeled data. So we will predict data based on a trained set on a data set that the algorithm has not seen before and see how the algorithm is performing. We will also compare two algorithms in the R programming language, the logarithmic regression and KNN. And as a result, we're trying to help you find the best machine learning algorithm for the prediction and to drive our marketing efforts. Without further ado, let us discuss the data. The data has a small number of variables. These variables have some missing fields, but a very minimal amount. It is maximum 40 per field. That translates in less than 1% of missing variable per field. The data contains different types of variables, such as character variables, for example, the browser. We have integer variables, such as the word count or the total images in an email. And we pre-process this data by eliminating the NA. We took the mean and we replaced these NAs, but we also made sure that it had the right number of digits, because, for example, number of images is 3. So if we were taking the mean, we had to make sure that it had no digits. So for 5 integer fields, we did that. The other character fields are taken care by the design treatment C that we used. This function is going to transform all those characters fields into zeros and ones so that the algorithm can understand these fields and use them in the computation. So next we will discuss, but before that, we also decided later on to remove the column sent hour, because this adds a lot of different variables of zeros and ones, as you can imagine, and that makes our algorithm clunky and it takes longer to run. So partitioning the data, partitioning is very important. Due to time constraints, we only chose to partition it in 2 sets. One is the train set, 90% of the data, and the other one is the test set, 10% of the data. This data set was also had the task of oversampling because it has a very low number of positives. We had to make sure that we perform this task. So we randomly partition the data set into train and test, and then we are ready to apply the first method, which is logarithmic regression. Now, we use the fit and the best fit to make sure that we reduce the number of variables. So we use the generalized linear model to predict, but before we did that, we had to fit the data, and we fit the data to remove the variables that were not relevant. When we use the best fit, we reduce the variables, but we were also using this function that you can see the graph here to figure out what's the best cutoff for the accuracies. The fit model cutoff was 75, the best fit was 0.7, but as we will explain later, perhaps 0.5 will be better. And I will pass to the next slide to show you what we did with the logarithmic regression. So we used the function to first on the planned data and then on the test data. So first, when we used the fit, it had 92 coefficients that included the centaur. It was hard for us to do a best fit on that because it was taking such a long amount of time that we had to only use 1% of the data. And as you can see, the 92 variables were still not giving us, they were giving us 70 for 50% cutoff and 11 for 75% cutoff. When we removed the centaur and then we tried to run the best fit, we called it best fit 2 and 3 respectively, we realized that yes, the cutoff that the function was recommended was 70%, but it didn't translate into a better test probability. You see the 75% still stayed 93%, whereas 70 was 92. But when you look, this orange here is what we recommend. It has a high amount of um, positive predictions. If you're using a more accurate one, you get very low prediction. You get like 17 and 13 respectively. So that's why we recommend the 50%. And the algorithm only has 12 coefficients because we removed the centaur. So we believe it's a elegant and nimble algorithm. Next, we will discuss the KNN model. So this model is computing the distances between all the variables. The variables have to be the same length, but because we use the Cariat library, it's pre-processing and it tunes and scales the length of each single variable to make sure that they're the same length to be used by the KNN. Now, we also use the tune length to determine whether we should go with a higher amount of neighbors, because first the algorithm is doing 5 neighbors, but when you use tune length 1, we weren't able to use tune length 10, which does 10 iterations on the whole data because it was taking probably days. So we only used it on 10% of the trained data, so 4,500 records. And that's where we had the graph that's telling us that perhaps 23Ks is good. But when we ran it overnight with tune length 5, we were told that 13 is a good K. So we will show you what that amount of neighbors does in terms of results. So we use the Caret library again, and that is automatically scaling the data. So the KNN results, as you can see, with a K of 5, you're getting about 50 positives that are accurate. There's 67 that are not accurate, that the algorithm says are positive. When you're using K13, yes, you're getting a much more high probability for both plan and test, but that translates to only 8 emails. So again, this might provide very low number of results. And the number of coefficients is 46. Now, we will compare it with what we showed you before, the best fit 3. And as you can see, that's why we recommend the orange that you see here, because it's giving you about 50 results on KNN that are accurate and 69 in the cutoff of 50%. So that's a reasonable percentage, keeping in mind that 7% was the actual percentage of clicks. So which model is best? Again, what we just explained to you, KNN takes a long time to run. If you consider the fact that if you're increasing the cutoff, you're probably getting only 13 clicks for the 500 emails that were predicted correctly, whereas if you use cutoff 50%, you get about 1.5. So that's about a fourth of the actual clicks. So that is a good prediction rate. And but you're also including noise. So you'll get another perhaps 60 to 70 clicks that are predicted as clicks, but they are not. So we have to keep that into account. That's why we're trying to put things into perspective. If you're using the KNN model, the 13Ks, you're getting about 1,000 emails for 300K, whereas you have 45,000 actual clicked emails. Now for 300, the logarithmic model would predict about 5K emails, but would predict another 5K wrong. And also it's important to think which model has the least amount of variables to avoid parsimony, which is having too many variables. So for next steps, we recommend you to consider improving the KNN by running with tune length of 10. It might take about a week with our current computers. We may consider using more powerful computers such as quantum computers to speed up processing time. We would want to deploy this model to run it on actual data and use the predictions to improve future emails and inform the CPM, the rate to charge the advertisers. So without further ado, if you have any questions, or if not, we would like to thank you very much for watching our presentation. Have a great day. Goodbye.